Welcome everyone, my name is Linyan Yang and today I have the pleasure of presenting our work Masking Image and Depth Features via Complementary Dropout for Domain Adaptive Semantic Segmentation. Semantic segmentation is a key task in a variety of different applications, ranging from medical image analysis to autonomous driving. It describes the task of assigning semantic classes to each pixel. While the computer vision community has achieved tremendous success in the past years, efficiently sourcing data for training remains an open issue, often requiring large amounts of human annotations. To reduce the amount of human labor required during training, researchers have turned their attention towards simulators, which can easily generate large amounts of annotated training data. However, while these images might seem similar at first glance, the underlying domain shift to real-world samples causes machine learning models to fail in most cases. In this example, we train a segformer model solely on a synthetic dataset agnostic to the target domain and deploy it in a real-world scenario. The network fails to bridge this domain gap and thus is unable to create a good segmentation map. Recognizing these issues, researchers explored unsupervised domain adaptation in an effort to bridge the gap between synthetic and real datasets. One popular approach focuses on self-training using pseudo-labels. Despite the success of these methods, we identified two major shortcomings. First, the current methods are unable to identify detailed structures, such as poles or traffic signs. Notably, this is still an issue even after applying high-resolution techniques. We further note that depth estimation methods are capable of recognizing these structures and may therefore provide necessary cues. Second, we observe that even with context clues, the model is prone to over-segmenting low-prevalence classes such as bus, truck, or train. Here we hypothesize that depth similarities may provide a strong cue for consistent semantic classes. To address these issues and findings, we propose MICDrop. Our proposed method is divided into two parts. First, we introduce a cross-modality feature fusion method for incorporating global and local cues. Secondly, we introduce a complementary feature masking strategy. The objective hereby is to withhold certain depth and RGB representations to encourage a more effective cross-modal feature learning and thus improve overall performance. To start, I will introduce our multimodal network architecture. For the RGB encoder, we utilize a segformer backbone. Contrary to other works, we initialize with UDA pre-trained weights instead of ImageNet weights. This allows us to effectively extract multi-level representations from the RGB inputs without the necessity of further training the RGB encoder. To introduce depth features, we utilize a slightly smaller hierarchical backbone. For initialization, we utilize ImageNet weights as these have learned spatial understandings of images. To fuse the multi-level representation from both encoders, we introduce a new feature fusion model. The fused features are then decoded using the respective UDA decoding head. Our cross-modal feature fusion module is composed of 3 blocks. Using a local self-attention module, we refine depth features in a local region. We then apply global depth-guided cross-attention to obtain image features based on the similarity of the corresponding depth features. We combine these refined features and feed them through our decoder head. While the aforementioned architecture allows us to incorporate the depth features, we notice that it underutilizes this information. To improve this, we introduce complementary feature masking. This strategy is comprised of 2 stages. First, we use blockwise dropout in the feature space. The goal here is to use larger blocks to prevent easy recovery from neighboring feature vectors of the same modality. Additionally, we use a complementary strategy to further force recovery from the complementary modality. In combination, our method is easily integrated into previously introduced network and training strategies, while requiring less computational resources compared to their base training method. For the main benchmark, we find that we consistently improve the performance of previous state-of-the-art methods. Further, we notice the plugin capabilities of this method by showing that our improvements are orthogonal to other context-enhancing or high-resolution strategies. To underscore our motivation, we utilize the boundary IOU to further demonstrate that both classes with fine structures as well as those prone to oversegmentation are improved. Qualitatively, we observe that our proposed method is indeed capable of improving segmentation performance for thin structures such as poles and traffic signs. Additionally, we also see improvements for larger objects such as fences. In summary, we noticed that recent UDA methods fail at fine structures and are prone to oversegmentation. We contribute by introducing a novel cross-modality feature fusion module and a complementary feature masking strategy. Using our method, we are able to improve results across UDA benchmarks and network architectures. Thank you for listening.